Hi viewer, my name is Miguel Recio-Poo, and today I will be summarizing one of my latest projects for the YouTube CMSA channel. This project has as title Hydration Accelerates Electron Hole Recombination in Small Titania Nanoclusters, and has been conducted here in the Universitat de Barcelona together with a group of Professor Alexey Akimov from the University at Buffalo. So let's start talking about the role of titanium in photocatalysis. Titanium dioxide, titania or TiO2, is a widely used metal oxide with important applications in both industry and environmental processes. One of its promising uses is in water splitting, which can generate hydrogen as a clean fuel. However, this reaction isn't spontaneous, it requires an input of external energy. One potential solution is using the anatase form of titania, which has shown good photocatalytic activity. But there are challenges. Titania has a large band gap, about 3.2 electron volts, which means it can only absorb a small portion of the solar spectrum, mostly in the ultraviolet. On top of that, it suffers from a high recombination rate of the electron hole pairs generated by light, which limits its efficiency. To tackle these issues, we studied excited state dynamics using nonadiabatic molecular dynamics, NAMD. This allows us to understand and potentially tune the electron hole recombination times, with the goal of improving overall photocatalytic performance. We will put special attention on the role of hydroxylation in this excited state dynamics, which, as far as we are concerned, is not yet observed in titania nanoclusters so far. So the methodology of this project is comprised by these 4 steps. First of all, we get the initial nuclear parametric trajectory of our titania nanoclusters. Then we compute with TEFT the excitations and get the excitation energies, the molecular orbital overlaps and time overlaps. Then, using the molecular orbital time overlaps, we compute the nonadiabatic couplings between states, and then using the NACs and the excitation energies from step 2, we can, following some trajectory surface hopping method, run nonadiabatic molecular dynamics to shed light finally in the excited state dynamics of titania systems. The 2 main codes using interchange in this methodology are CP2K and Libra. And the systems that we have used or we have worked with here are 3 titania nanoparticles of 8 molecules with different degrees of hydroxylation. So bare case without water molecules, a middle hydroxylated case with 2 water molecules, and a fully hydroxylated system with 5 water molecules. So I show here first the results from step 1. So 2 different approaches have been followed for the molecular dynamics: classical dynamics with well parameterized interatomic potentials such as nanotio and FFTIOH, and also the more expensive ab initio molecular dynamics with PBE, so DFT, for modeling the interaction between the atoms. We have run 4 picoseconds, and we have sampled the last 3 picoseconds for the following steps, and as the time step was 1 femtosecond, we have 3000 structures. So in this left-hand side plot, you can see the vibrational modes that we get after computing the power spectra of the molecular dynamics, and we see the typical TiO-Ti angle bending and typical TiO stretching modes in the typical values associated to these modes. Also, when adding a certain degree of hydroxylation, in this case 5 water molecules, we see that the characteristic hydroxyl stretching modes around 4000 centimeters to the -1 appear for both ab initio and force field molecular dynamics runs. And all in all, there's a good agreement between these 2 approaches, which points toward the use of force fields as they are a much less expensive way of computing the molecular dynamics. So now I show here the results from step 2. After computing the TEFT excitations, it is important to remark that we include up to 10 TEFT excited states, but we are just modeling the transition between ground state S0 and the first excited state S1, because we want to model the recombination between the electron and the hole, and working with these 2 states is enough to model that. We use PBE, PB0 and B3lib as functionals, and we get also in this case the time overlaps between consecutive geometries. So, as we can see here in this plot, hydration increases the excitation energies, and also we see how hybrid functionals mitigate the classical PB or GEA underestimation of the excitation energies. Besides, we compute also in this case the influence spectra, that is the Fourier transform of the correlation function of the energy gap fluctuation, and we see how, importantly, the transition between S0 and S1 is driven by bending and stretching TiO modes. So it seems that the hydroxyl related modes are not directly coupled to the transition they are there in the right hand side of the right hand side plot, but they are not colored because they are not activated, or they are not associated to this transition between ground state and first steady state. So with the molecular orbital overlaps and the time overlaps that we have computed in the previous step, we can now, following the Hamesh-Schiffer-Tully approach, compute the NACs, the nonadiabatic couplings between ground and first steady state, and we see that going from 0 to 2 water molecules, there's a competition between the energy difference and isotropy, but in general the NACs go down, which is kind of reasonable if we look at the energy gaps from the previous slide, or the first steady state energies. We saw how the energies go up a little bit going from 0 to 2. So as the levels or the states are more separated in energy, the NACs are lower because they are not that well coupled. However, we see, surprisingly, that when we go to 5 water molecules, the NACs increase, and the energy of first steady state increase as well. So we would expect the opposite, but we justify this with not just the energy difference between the levels, but also the HOMO and LUMO charge distribution. And we see here how for the 5 water molecules it is like more spread, the distribution of these orbitals, and also more isotropic. So this means that it mixes better and it enhances the nonadiabatic couplings, something that was not happening in the other cases. So this may suggest that when increasing the degree of hydroxylation, the recombination is faster between the first and ground states, since they are more coupled, as we can see here in the ultimate case with 5 water molecules. To see this, we compute the nonadiabatic molecular dynamics using as input some values obtained in the previous step. The energies of the first steady state, the couplings between 0 and 1 are used to construct the vibrational Hamiltonian at every step. Then we employ several trajectory surface hopping algorithms. In this case I will show just the MSDM, one approach that includes electronic decoherence between energy levels, and we initialize a bunch of trajectories in the first steady state. So we analyze how the population decay from the first steady state to the ground state. We use this exponential fitting function, and importantly we see how, as we include more and more water molecules, their recombination time decreases. So the recombination rate is bigger when we include more and more water molecules. This is the key result from this paper. You can see here how the population of the ground state at the beginning is 0, but then when the recombination time proceeds or increases, the population grows faster in the orange shade region, which is associated to the larger degree of hydroxylation. And I will show here some numbers, and we see that in the 3 cases with PB, PB0 and B3 lip, the recombination time, the ground state population recombination time decreases faster and systematically in all cases. So the conclusions of this work is that Libra, interchanged with CP2K, provides a complete workflow to analyze steady state dynamics in titania systems. Then that the influence of water increases excitation energy and generally NACs, but it is an indirect influence because the hydroxyl are not coupled to a transition, as I showed in one of the previous slides when I showed the influence spectra. More importantly, hydration increases electron-hole recombination rates, which is a key result that has not been observed in the past. And from a methodological point of view, we see how hybrid functionals and decoherence corrected methods produce accurate predictions compared to other, let's say, not that expensive methods. And we see a very good agreement, a very strong agreement between force field and ab initio, which points towards the use of force field, as they are a cheaper option compared to the use of ab initio methods. So with this I finish. I would like to say thanks to my supervisors, to my tutor, also to Professor Alexey Akimov from the University at Buffalo, and of course to the different agencies for funding my project during all these years, and of course of you for your kind attentions. See you soon. Bye bye. Thanks.